So now that we know how to identify ionic and molecular compounds, and we took a look at naming some simple ionic compounds, we also need to figure out how to balance out these charges. If we're just given the ions and asked what would the ionic compound form that would be. So the quick way that I showed you in the previous module was by simply taking those charges and making them subscripts when those two ions come together. So here I've got magnesium nitride. I've got magnesium at 2+, and I've got nitride at 3-. So when they come together, the charge on magnesium, that number 2, is going to become a subscript on nitrogen. And the 3 on nitride is going to become a subscript for magnesium. And again, we can break this down the same way we did with aluminum oxide to show this is what you need for this to be a neutral ionic compound. So magnesium is 2+, and I have 3 magnesiums. Got 2 nitrogens at 3- each. So 3 magnesiums, each having a 2+ charge, is +6. 2 nitrogens at 3- each is -6. I add that together, I've got a charge of 0. We always need to have our charges add up to the charge on the ionic compound. And so in this case, it's a neutral compound. Those charges need to add up to 0. So we need to balance out those charges, and that's going to help us determine what is the ionic formula for this compound. So here's some practice with you. And again, this is why I said it was important to kind of know the charge on each group. We said group 1 will always carry a charge of +1. Group 2 will always be +2. Aluminum is the only one we're going to look at from group 3. That would always have a +3 charge. And then for the nonmetals, right, nitrogen would have a -3 charge. Oxygen is going to have a 2-, and our halogens are going to have a -1 charge. And don't worry about the transition metals yet. We will get there, but there'll be multiple charges. So sodium and sulfur. What would the ionic formula be of sodium and sulfur? Well, sodium is +1, and sulfur is 2- as an ion. So that means I would need to have 2 sodiums to balance out the charge from sulfur. So sodium sulfide would be Na2S. Magnesium and bromine. Magnesium is group 2, so it's going to have a +2 charge. Bromine is group 7, -1 charge. So magnesium bromide would be MgBr2. Calcium oxide. So calcium is group 2, that's +2. Oxygen is -2, so calcium oxide. Aluminum and chloride. So aluminum is +3, chlorine is group 7, so it's a -1 charge. Aluminum chloride. I would need 3 chlorides to balance out the charge on aluminum. Aluminum and sulfur. So aluminum sulfide, aluminum is still 3+, sulfur is 2-. So again, by making this charge a subscript, I would need Al2S3 for aluminum sulfide. So we should be able to go from the elements to the formula to a name, or the name to a formula. And again, you do not need to memorize the charge for each individual element, but you should know the charge on group 1. You should know the charge on group 2. You should know the group charges for the halogens, oxygen, sulfur, selenium, and tellurium, because that's going to help you be able to put together these ionic formulas. So at first I said don't worry about the transition metals, because the transition metals will have a variety of charges. That's where the periodic table can get pretty complicated. We're going to just look at a few examples from the transition metals because of these multiple charges. So for example, iron. I could have 2 different states of iron. I could have iron 2+, I could have iron 3+. We're also going to look at copper. Copper could be +1, copper could be +2. Because there are multiple oxidation states available for these transition metals, we need to have a little bit different way of naming them so we know, am I using copper 1, am I using copper 2, or am I using iron 2, or am I using iron 3, because that will change the formula. For example, if I said I had iron chloride, well, I could think of two different ways of writing that. I could think of iron chloride, I could think of iron chloride, right? That's a problem because they have a different formula. And so it's going to depend on, am I using iron 2 plus? Am I using iron 3 plus? Because depending on the form of iron I'm using, that's going to change how many chlorines I would need to react with to form a neutral compound. So we need to change the way we name transition metals to indicate what charge am I working with, because that will certainly change the elemental formula. So if there is only one cation that can be formed, right, then we're safe with the way we name ionic compounds. We're safe by just saying the name of the metal followed by the name of the nonmetal. So for example, sodium. Sodium is a metal. It can only take a charge of +1. So if sodium is in an ionic compound, we would always just say, okay, yep, I'm working with sodium. And we would all know, okay, sodium as an ion is +1 charge. Another example from a transition metal now is silver. Silver only occurs in the +1 oxidation state. So when we're naming something with silver, I can just say silver, and we'll all know silver has a +1 charge in the oxidation state. However, when we're working with a transition metal that has multiple charges available, we have to use the Roman numeral in parentheses to indicate what form are we using. So for example, if I had iron 2, when I'm naming a compound that has iron 2 in it, I would say iron 2. Or if I was working with iron 3, I would say I have iron 1, 2, 3. So when we have multiple charges available for an element, we're going to use these Roman numerals to indicate what form of that element am I using. Am I using iron 2 plus or am I using iron 3 plus? The same thing would apply for copper. So if I had copper 1, I would just write in the name, I have copper 1. Or copper 2, I would say copper, Roman numeral 2 in that name. And so that helps us now clear up FeCl2 versus FeCl3. To name iron chloride, I would say I have iron 2 chloride versus FeCl3. Now I have iron 3 chloride. That Roman numeral indicates to us in the name, okay, the charge on iron is 2 plus. Because iron is 2 plus, I would need 2 chlorines at -1 each to balance that out. Iron 3 chloride, the iron must be 3 plus, so I would need 3 chlorines to balance out that +3 charge on the iron. So if we're using a transition metal where multiple charges are available, we need to use the Roman numeral to indicate what form are we using. Are we using +1 or are we using +2 or +3 in the case of the iron 3? Okay, so let's take a look at some examples to figure out how we would name these compounds. So we look at this, we've got iron 2O3, Fe2O3. Okay, well, iron can be two different oxidation states. Iron could be +2, iron could be +3. The one thing we do know for sure, though, is oxygen. Oxygen is always 2-. And so if I break this apart, I have 2 irons and I have 3 oxygens. Oxygen is always 2-. So if I have 3 oxygens at -2 each, I've got a charge of -6 from oxygen. That must mean, to balance this out, I would need a charge of 3 plus on iron. So I would name this compound iron 3 oxide. Ruthenium chloride. So to name that correctly, I've got 3 chlorines at -1 each. So that's a charge of -3. So ruthenium must be +3. So I would say I have ruthenium 3 chloride. Again, we're not sure maybe the charge on palladium, but we do know sulfur. Sulfur is in the same group as oxygen. Oxygen's -2. Sulfur is also -2 as an ion. So I've got palladium and I've got sulfur. We said sulfur is -2. I have one of those, so palladium needs to be +2 to balance that out. So palladium 2 sulfide. And the last one, manganese and oxygen. Again, we break this down. I've got 2 oxygens at -2, so that's a charge of -4 on the oxygen. So manganese must be 4+. To give me manganese oxide. So you might not know the charge on iron or the charge on ruthenium or palladium or manganese. What you definitely need to know, though, would be the charge on the nonmetal, on oxygen or chlorine or sulfur, because you should know, right, the group they're in and the periodic table. Because you know the group they're in, you should know the charge. And if you know the charge on half of the compound, right, you could figure out the other half, like we did in this case. I don't know what form of iron I'm working with, but I know the charge on oxygen is -2. I have 3 of those oxygens for a total charge of -6. So to balance that out, right, we decided that the iron needed to be +3. Polyatomic ions are the last ions that we're going to look at in helping figure out how to name different compounds. So polyatomic ions are unique in that they are molecular. They are held together. They're different elements held together by covalent bonds, but they carry an electrical charge. And again, you probably know some of these because you've heard of things like hydroxide or nitrate or phosphate or sulfate. Those are examples of a polyatomic ion. When we're using polyatomic ions in nomenclature, it's just going to be what's the name of the metal followed by what is the name of the polyatomic ion that we're bonding with. And again, we do not need to know this entire chart, but you'll definitely see things like carbonate. You'll definitely see things like sulfate and phosphate and hydroxide and nitrate. And then for the positively charged polyatomics, you'll definitely see things like ammonia. So it's good to know a few of these. Acetate as well shows up. So you will want to know a handful of these polyatomic ions. It'll just help in nomenclature and naming a compound that contains a polyatomic ion. So when we're naming with a polyatomic ion, it's just like ionic compound. What's the name of the metal, followed by what is the name of the polyatomic ion. And remember, the metal comes first, so what is the name of the metal as an element, followed by the name of the polyatomic ion. So the first one, I've got sodium and I've got sulfate. So sodium, sulfate. Down here, I've got silver and I've got cyanide. Here, I've got calcium, carbonate. Up here, I've got sodium sulfite. Sulfite has one less oxygen than sulfate. The ITE ending of sulfite indicates I've got one less oxygen than sodium sulfate. ITE for sulfite. cadmium and a hydroxide. And the last one, I've got potassium phosphate. And again, we should be able to break these down and figure out the charges on each of these. And so, for example, potassium is group 1. So we're going to look at potassium phosphate. Potassium is group 1. So that means I've got 3 potassiums that are +1 each. So 3 times +1, I've got a +3 charge. The charge on phosphate needs to be 3- to balance that out. So again, I don't expect you to know the charges on all the polyatomics, but you should be able to break it down in this way, that you know potassium's group 1. I have 3 potassiums at +1 each. To balance that out, phosphate, PO4, needs to be 3-. We could do the same thing here with calcium carbonate, right? Calcium is group 2. So calcium carbonate is going to break down into calcium 2+. Because calcium is 2+, the carbonate needs to be 2-.